All right, this is Honors Algebra 2 Pre-Calculus. We're doing 8.5 in Algebra 2, and we're solving rational inequalities by hand in this video, which is the second in the series. So the book teaches this particular scale in a particularly not clever way. It's fine if you want to look through how the book does it, and there's nothing wrong with the way the book does it, but I think that in the long run, for very simple problems, it works fine. For very complicated problems, it makes the situation untenable, right? Which is another way to say not manageable. Comes from the Latin teneo, tenere, which is to hold, right? So it's something you can't manage for difficult problems. So the easiest way to solve rational inequalities by hand is to make the right-hand side 0 and clean up the left-hand side into a single fraction. Once you've done that, you can use a sign chart to quickly determine which intervals satisfy the inequality. This is way faster and more effective than the method in the textbook, especially for harder problems. For easier problems, the method in the textbook's not awful, but let's go ahead and walk through this. All right, so here's what we're going to do. Remember that 0 is a special number, right? 0 is a number that when you multiply or divide to get 0, well, you can divide to get 0, but when you multiply or divide and have 0, it tells you things about the numbers involved, right? If a times b equals 0, then either a or b is 0, and that doesn't work for other numbers. If a times b is 8, I know nothing about a and b except that they multiply to 8. I don't know anything individually about a or b. So here's what we're going to do. When we solve rational inequalities by hand, we're going to make the right-hand side equal 0. So I'm going to do that by subtracting the 1 over, okay? I'm going to subtract the 1 over. And then what I'm going to do, I'm going to go ahead and call it a 1 over 1. I'm going to get a common denominator. So I'm going to say, hey, this guy's denominator is a 2x minus 1. I need a common denominator. And I promise I'll show you how this works in multiple videos, not just this one. So I'm going to get that this is an x minus the quantity 2x minus 1, right? Because there's a minus in front of that. All over my nice, happy common denominator is less than 0. When I clean this up, I'm going to get that this is a negative x plus a 1. So negative x plus 1 on top of a 2x minus 1 is less than or equal to 0. Okay, so here's the cool thing. I can solve this with sign charts, right? So see how this is a single fraction, okay? So I'm going to find the spots that make the top or bottom 0. So we're going to use a sign chart. Remember that less than or equal to 0 is the same thing as saying negative or 0, right? We want to find when this thing is negative or 0. That's what less than or equal to 0 means. So we're going to use a sign chart. When we use a sign chart, we need to set each factor equal to 0. So negative x plus 1 is 0, x is 1, okay? That's one of the values on my sign chart. Or 2x minus 1 is 0, so x is 1/2. When I make my sign chart with these two values, so my negative infinity, here's my 1/2, here's 1, here's infinity. I put both factors on the sign chart. So here's my negative x plus 1, and here's my 2x minus 1. I want to know what their quotient does, right? If you do this divided by this, right? So negative x plus 1 is a line with a negative slope. See how there's a negative in front of the x? So it looks like this, meaning it's positive before it crosses 0 and becomes negative after. So it crosses 0 at 1, it'll be positive and turn to negative. Now, if you don't like that logic, you don't have to use the logic. You could just pick a number. Try plugging in the number 0, right? The number 0 would fall right here. If you picked 0, you'd get 0 plus 1, which is positive. Right? If you picked 3/4, you'd get negative 3/4 plus 1, which is positive. But if you picked 2, you'd get negative 2 plus 1, which is negative, right? You could just pick numbers to plug in. 2x minus 1 is a line with a positive slope. We know it's 0 at 1/2 because we already did the work to figure that out, right? Because it's got a positive slope, it's negative, crosses the axis at 1/2 and becomes positive. Now, if you don't like that logic, you can plug these numbers in. If you plug 0 in, you're going to get 0 minus 1, which is negative. If you plug in 3/4, you're going to end up getting 3/2 minus 1, which is 1.5 minus 1. That's positive. If you plug 2 in, you're going to get 4 minus 1, which is positive. Now, remember that what we're doing here is we're dividing, right? Negative x plus 1 over 2x minus 1. Well, we already know the signs of those things, and because this is just division, signs are all we need. This is going to be a positive divided by a negative, which means it's going to come out negative. This is going to be a positive divided by a positive, which means it comes out positive. And this is going to be a negative divided by a positive, which means it comes out negative. So my answer are the intervals where I have negative values, and also intervals where this thing equals 0. It's important to notice that this 1/2 is a vertical asymptote. So while this function is 0 here, it's not 0 at this line. It's not 0 at the line because that's a vertical asymptote. So my answer should turn out to be negative infinity up to 1/2, but I can't include 1/2 because it's a vertical asymptote. And then again, from 1 to infinity. Now, there are other ways to figure this out logically, right? But I'm going to say that this is arguably the best way to do it. Now, there's totally other ways. Your book shows it in a different way, and that's fine. I am going to walk through the way that your book shows it. On a problem of this level, it's doable to solve it with the book's method. It's even on this level, which is an easier problem, it's very lengthy. So let's walk through how your book does this, just to give you an idea, okay? And again, your book's method's not wrong, right? I would argue that it's just really tedious, and without a calculator, you're going to find yourself in a bit of a spot on a harder problem. So here's how the book does it, right? So the book, here's the book's method. And I'm not going to do this on every problem, but I just want to show you what we're talking about. The book's method is to recognize that this is a variable expression, right? It varies. So remember that what we would normally do, if this was a fraction and it didn't have an inequality, you would just multiply the 2x minus 1 over, and that would be fine, right? So the logical step would be to multiply this over. The problem is that, remember, when you multiply by a negative, you have to flip the inequality sign. So if 2x minus 1 is positive, meaning if x is greater than 1/2, then when I multiply it over, I get x is less than or equal to 2x minus 1, which is fine. But if that 2x minus 1 were negative, right, meaning if x is less than 1/2, then when I multiply that quantity over, it's going to flip the inequality sign. So what's going to happen is I'm going to end up with two scenarios. So if I move this over to solve, I get negative x is less than or equal to -1, x is greater than or equal to 1. So these two things have to be true together. So if x is greater than 1/2 and at the same time x is greater than or equal to 1, well, if we look at that on a number line, here's 1/2, here's 1, this one looks like this one looks like this. Since they both have to be true, right, because this statement can only happen if this were true, then my answer ends up being this chunk. So I end up getting that on this half, x is greater than or equal to 1, or the other way to write it is 1 to infinity, right? On the other side, if I'd gone the other direction, if I solve, I get negative x is greater than or equal to -1, x is less than or equal to 1. Well, again, both of those things have to be true, right? Because I was only allowed to solve this way if x was less than 1/2. So if we look at what this looks like, here's 1/2, here's 1. This one looks like this one looks like this. Since it's both of them true at the same time, this has to be my window. So I get x is less than 1/2. The other way to write that is negative infinity to 1/2 with a parenthesis. And together, those two give me my answer. And if you look, those are the same answer we got when we did it my way at the top. It's the same amount of work. The difference is that while my method might look a little bit more intense up front, on a harder problem, my method's going to prove a lot easier than having these different cases. So in this instance, you had to have two cases depending on whether this denominator was positive or negative. If I give you a problem where there are multiple denominators and you have to deal with multiple cases, it can get really complicated really fast. All right, so go ahead and give this a try. You can do it my way or the book's way. I really don't care, but I personally am going to advocate for the way I do it, but it's your business. Okay, so the way that I would do this is I would move x minus 1 and x plus 2. I'd subtract a 3 over 1 is less than 0, right? I'd then get a common denominator to make this a single fraction. So I'm going to multiply this by x plus 2 over x plus 2. I'm going to get x minus 1 minus the quantity, minus the 3 times the quantity x plus 2, all over an x plus 2 is less than 0. And when I clean up the numerator, this is a negative 3x minus a 6. So I think I get negative 2x minus 7 all over an x plus 2 is less than 0. So this is what I'm going to be working with, right? So I'm now going to use a sign chart to see when this thing is negative, right? Because that's what less than 0 means, right? So that's what I want. I want when this thing is negative. So I would find my zeros, negative 2 x minus 7 is 0, negative 2x is 7, so I get x is negative 7 halves. Or x plus 2 is 0, I'm going to get x is negative 2, and I'm going to make the note that this is a vertical asymptote. So when I make my sign chart, these are the two values that are going to go on my sign chart. So here's my negative 2, which is a vertical asymptote. Here's my negative 7 halves, because that's a negative 3.5, right? Okay, so when I list my factors, I have a negative 2x minus 7, and I have an x plus 2. Negative 2x plus 7 is a line with a negative slope, right? We know it's 0 at 7 halves because we just did the work to find that, and because it has a negative slope, it starts physically above the axis, crosses that 0, and then drops below. So it's going to go from positive to negative. If you don't see that easily that way, pick an easy number. Try a negative 10, right? Try a negative 3, and try a 0. Plug in numbers. If you plug in negative 10, you're going to get a positive 20 minus 7, which is 13. That's positive. If you plug in negative 3, you're going to get a positive 6 minus 7. Well, that's negative. And if you plug in 0, you're just going to get a negative 7. If you do the same thing with x plus 2, remember x plus 2 is a line with a positive slope, so we know it's 0 at negative 2. It's negative and then crosses the axis to become positive. That's how lines with positive slope work. So it's negative and then positive. But if you don't see that, it's fine. Plug in the numbers. Negative 10 plus 2 comes out negative. Negative 3 plus 2 comes out negative, and 0 plus 2 comes out positive. Remember that I'm dividing, right? So it's this thing over this thing. So I'm going to get positive over negative. Well, that's going to come out negative, right? I'm going to get negative over negative. That comes out positive. And I'm going to get negative over positive. That comes out negative. Since I'm looking for where the answer is negative, I want these two spots, right? But remember, you can't include the vertical asymptote. So this guy was a vertical asymptote. And actually, it won't matter in this point at all because neither is included. So never mind. It doesn't really matter. So my answer, right, since it doesn't say equal to, I don't really have to worry about the asymptote too much. Negative infinity to negative 7 halves, and again, from negative 2 to infinity, right? Those are when those answers are negative. Now, if we walk through the book way, and I really am going to stop the book way after this particular example because the book's way is disgustingly difficult for the example after this, which is sort of the reason I want you to get to know my way, because when you see the harder examples, you'll kind of get why the book's method is not really manageable for harder things. If you do it the book's way, right? So that was my way. If you do it the book's way, there's nothing wrong with it. It just gets much more difficult. Remember that you want to multiply this thing over, right? But this thing varies, right? That's the idea of a variable expression. So there's two possibilities. If x plus 2 is positive, right, meaning x is greater than negative 2, then when I multiply that over, the sign doesn't change direction, right? So I get x minus 1 is less than 3x plus 6. Negative 2x is less than 7. X is greater than negative 7 halves, right? So if I put those two together, because they both have to be true together, right? So I have x is greater than negative 2, and if that's true, then x must be greater than negative 7 halves. Well, when I put those together on a number line, negative 7 halves, negative 2, the window where both of those things are true is right here. So the answer I get from those two together is from negative 2 to infinity, right? If we did the same thing over here, but with the negative case, so if instead that variable expression had been less than 0, meaning if x is less than negative 2, well then when I multiplied it would have changed the direction of the sign, so this would become greater than, right? Because if I multiply by a negative, it changes the direction. So x minus 1 is greater than 3x plus 6, right? When I add the 1 over and subtract the 3x over, I have a negative 2x is greater than 7, so x is less than negative 7 halves, right? Well, if both of those are true at the same time, so x is less than negative 7 halves, and at the same time x has to be less than negative 2. Here's my negative 7 halves, here's my negative 2. Both of them have to be true at the same time. That's this window here. So I get from negative infinity to negative 7 halves, and those two together are my intervals. Well, that's the same intervals I got my way, right? So again, a different way to do it, but the same concept. Now, as we approach the harder problems, I want to point out why my way is a lot easier. So if you tried to do the book's method now, you'd actually have to have 4 different cases. What if the x minus 3 is positive and the x plus 3 is also positive when you multiply the denominators over? What if this one's negative but this one's positive? What if this one's positive but this one's negative? What if they're both negative? It becomes very, very difficult. So as you do a problem like this with multiple denominators, the best option, so your textbook actually doesn't even give an option to do this one, or maybe they do give the option to do it by hand, but say that it's a terrible plan, which it is. It's not as bad if you do it my way. So let's go ahead and do it my way. We're going to move everybody to one side. Again, I'm not saying it's fun, but and we're going to go over how to do this on a calculator in the next video. This is at least an easier way to do it. So this is asking us for when is it positive. That's the question we're being asked. So I'm going to get a common denominator so that I can use a sign chart. You can only use a sign chart if you're dealing with multiplication and division. And right now I am not. I've got subtraction here, right? So the common denominator I'm going to need is this entire thing is going to have to multiply this denominator, or this fraction, right? And this entire thing is going to have to multiply this fraction. And that looks disgusting, but it's not as bad as it looks. So let's go ahead and do some super intense, awesome math. So when I FOIL the top here, I have an x plus 3 times an x minus 2. So that's going to be an x squared plus an x minus a 6. Minus, when I distribute this, this is a negative 2x times this x minus 3. So I'm going to get a negative 2x squared plus a 6x. And then on the bottom, I have this 2 times an x plus 3 and an x minus 3, which I definitely want to leave factored because it was very nice of them to already factor it for me. So on top, I seem to get a negative x squared plus a 7x minus a 6. And then I have a 2 and an x plus 3 and an x minus 3, still trying to show that it's positive. Now, I don't like having a negative leading coefficient, so I'm going to yank out a negative 1 and make this x squared minus 7x plus 6. So I end up getting that this is a negative 1, x minus 1, x minus 6, all over a 2 times an x plus 3 and an x minus 3. And I want when this thing is greater than 0. So I need to find all those spots where things are 0, right? So negative 1 equals 0 is a lie. X minus 1 equals 0 is going to give me a 1. X minus 6 equals 0 is going to give me a 6. 2 equals 0 is a lie. X plus 3 is 0 is going to give me x minus 3 is negative 3. X minus 3 is 0 is going to give me x is a positive 3. So these are the factors that need to show up on my sign chart. All of them, including the negative 1 and the 2, especially the negative 1. The 2 is not going to make a bit of difference, but the negative 1 is going to make a difference. So let's go ahead and clean this up. So I have 4 numbers that need to come up at the top of my sign chart, right? I have a negative 3, a 1, a 3, and a 6. So negative 3, 1, 3, 6, and infinity. All right. My factors are a negative 1 and a 2. I'm going to put both of those on right away. An x minus 1, an x minus 6, an x plus 3, and an x minus 3. And it's worth noting that the 3's, both of them are the vertical asymptotes. So both of these are vertical asymptotes. It's a problem if I'm trying to find values. So when I make my sign chart, maybe you've noticed it doesn't really matter if you notice which ones are on the top or the bottom so much, except for in terms of vertical asymptotes. It really just matters how many negatives and how many positives you get. So a negative 1 is literally always a negative 1, which is why it needs to go on the sign chart, because those negatives are going to change signs of things. The 2 is literally always a positive 2. It doesn't need to be on there as desperately because honestly, the positives don't change signs. Okay, so all of these are lines with positive slopes. They all look like this, right? They all are lines with a positive slope, meaning you could find numbers to plug in, but all of them are going to find their 0. So x minus 1 is 0 at 1. It's negative before it hits that 1 and positive after because it's below the axis, crosses 0, and ends up above the axis. X minus 6 is 0 at 6. And again, it's going to be negative for any number you plug in before 6 and positive after because it's negative, crosses the axis, and becomes positive. X plus 3 is 0 at negative 3. It's negative before it crosses that 0 and then crosses above the axis and becomes positive after. And again, you can plug in numbers. I don't care, but you certainly don't have to. And then x minus 3 is 0 at 3. It's going to be negative before it crosses that 0 and positive after. So then really all I'm doing is playing a count the negatives game. If there's an odd number of negatives, this thing's going to come out negative. 1, 2, 3, 4, 5, this thing comes out negative. 1, 2, 3, 4, it comes out positive. I really just have to count the negatives. 1, 2, 3 comes out negative. 1, 2 comes out positive. 1 negative comes out negative. I wanted when is this thing positive, so my answer are these two intervals. So my answer is going to be -3 to 1, and again from 3 to 6, and that's my answer. And we're going to talk about how to do these on a calculator in a minute. The book's way of doing this, which it does show you on one of the textbook pages, is the same basic idea as these problems where we had 2 cases, except you're going to have 4 cases because you have to be concerned with both denominators being either positive or negative, right? This could be positive with this positive. This could be positive with this negative. This could be negative with this positive. This could be negative with this negative. And it's going to make a lot of cases and it's going to be really hard. So I definitely am not saying that my method's easy, but it is quicker than the other option if you don't have a calculator. All right, so we're going to do one last problem like this, and then we're going to switch to how to do these on a calculator. All right, so you're going to give this a try. Now this one's slightly nicer, right? I gave you the slightly nicer one because they are the same denominator. So I'm going to go ahead and move this over to the other side, and I want when this is less than 0. So this is saying, hey, when's this negative? Conveniently, they already have the same denominator. So when I put them together, I'm just going to get x plus 1 minus x over this x minus 1, right? Which seems to give me a 1 over x minus 1 is less than 0, right? So this one's actually going to be pretty easy, and you could arguably do this without the sign chart, depending on, sort of where your skill set's at. But so I either want 1 to be equal to 0, which is a lie, or x minus 1 is 0, which is x is 1. So the only number that needs to go on my sign chart is that 1. My factors are the 1 on top and the x minus 1 on the bottom. 1 is always positive, and x minus 1 is 0 at 1. Since it's aligned with a positive slope, it will start negative and become positive. Again, if you needed to see that, you could try plugging in numbers like 0 and 2, right? What that means is that a positive divided by a negative will come out negative, and a positive over a positive comes out positive. This is the answer I want. My answer is going to turn out to be -∞ to 1. And that's it. All right, so we're going to go into how to do some of these harder ones, especially one like E4 on a calculator in the next video.